Hello, my name is Robert C. Gray, and I'm a PhD candidate in digital media at Drexel University. And on behalf of my co-authors, today I'm going to be talking about our research on the use of multi-arm bandits, or MABs, toward multiplayer modeling. We'll start off with how we use MABs for player modeling in general. An MAB problem is a type of sequential decision problem where an agent is faced with many potential choices, which we call arms, and it has to repeatedly select or pull from these arms, yielding some reward from an underlying and unknown distribution. And the agent wants to maximize its total reward across all pulls over the length of its horizon, and for each pull, the agent has to choose between exploring the arms to get a better sense of their reward potential and exploiting the arm that it currently thinks is best. We've seen MABs used successfully for player modeling in the past, including our paper published last year here at COG 2020. So we give a player the first option for a gameplay experience. We'll call it Arm A, which we believe appeals to a certain player type, and we will then see a reaction from the player in terms of a response metric, maybe something like their playtime or their use of a feature. And the next time we give them the second option, Arm B, and Arm C and D and so on until we build an idea of which option yields the best response. And through that, the player receives their designation within the model, and the agent will become more capable as it makes more observations. In this way, the method is the model. And the same tool that we're using to perform the game adaptation is simultaneously the tool that is modeling the player. Well, now let's say we want to model a group of players. Maybe it's a multiplayer game and we want to adapt the game for the group, or maybe we want to model a player quality that only manifests in a group setting, like leadership or team cohesion. But now if we're adapting our solution to a group of players, our approach faces some new challenges, where each arm represents a single way of modifying the game, but the modification is made for all players simultaneously. And we find that moving to this new application requires us to rethink both what exploration and exploitation mean in this context. Specifically, we see three new design challenges here. First, we need to reevaluate how we perform best choice estimation. With single players, we're able to make straightforward inferences from the rewards to make future predictions, but when dealing with multiple sources for a reward, how do we best aggregate them to determine which arm is best? And second, we need to reevaluate how we approach exploration. MABs have to sometimes select less explored arms to better understand their potential, but now that we have multiple players, the selected arm may not have a direct one-to-one relationship with the experiences of all players. So to properly explore for a group, we need to consider how that affects our approach. And third, we need to consider social fairness. If all we consider is maximizing reward, the agent might tend to favor a choice that benefits certain players, and other players might be ignored or marginalized. With all the players under the care of the AI, we have to recognize the AI's responsibility for ensuring that players receive equitable consideration. And today we'll be talking about our solution for number one, which is the multiplayer regression oracle, or MRO, and our solution for number two, which is an approach we call multiplayer forced exploration, or MFE. And our future work following this publication is addressing challenge number three, social fairness. And as for our motivating domain, we work with lifestyle exergames, where we design software interventions that aim to motivate players to increase the number of steps they take in their daily lives, as measured by a pedometer. Our current research examines the psychological phenomenon of social comparison. Specifically, we aim to model a player's social comparison orientation, or SCO, toward game adaptations that can motivate the player. So what is SCO? We understand from psychology literature that people frequently compare themselves to others, consciously or subconsciously, and these comparisons render different effects according to a person's SCO. Some, when confronted with another who's outperforming them, and we call these upward comparisons, will find it inspiring and motivating. They just need to try harder. On the other hand, some may be discouraged by upward comparisons because they don't believe they could ever achieve that for themselves. And the same is true for downward comparisons. Another performing worse might be viewed as inspiring to avoid the same situation, or it might be used as an excuse to relax. A person's SCO will determine their general tendency to be motivated and demotivated by these upward and downward comparisons, and the idea is that if we could model a player's SCO, it could be a motivating force. And we've demonstrated that this is possible in previous experiments for individuals, where we fabricated artificial teammates alongside human participants to create upward or downward comparison opportunities in terms of daily step performance. And we found we could increase their motivation to walk more. So we modify this for a multiplayer scenario. Two players with their previous day's steps engage in an exergame activity together, along with a third teammate that, not known to them, is fabricated by the MAB agent. When the agent creates the player, it can give them any number of steps, placing them above, between, or below the performance of the two players. And this placement would provide extra upward and or downward comparison opportunities for the players, which ideally would appeal to their SCO and provide motivation. This scenario becomes the testbed for our current investigation, where we create a simulation with virtual players that are given both a daily step generator and SCO parameters that dictate their tendency to react, by being motivated or demotivated, to comparison opportunities. For the sake of time, the details of both the step generator and the SCO parameters are explained in detail in the paper and also our previous work. So, in our simulated exergame activity, two virtual players show up with their previous day's steps, along with a third player generated by the MAB agent that is above, between, or below the virtual players in terms of its achieved steps. Following the activity, the virtual players go on with their virtual day, achieve some number of steps that the MAB observes based on their reaction to the activity, and return to repeat the exercise a given number of times. And of course, the MAB agent never gets to know the underlying SCO parameters of either virtual player, like that's the whole modeling exercise. But the AI will attempt to figure them out via experimentation and find the combinations that maximize the resulting steps for both virtual players over time. For the AI, we formulate this problem as an MAB problem with 4 arms. Arm A places the fabricated teammate steps 20% above the higher of the two virtual players. Arms B1 and B2 place the fabricated teammate steps between the others. B1 is available when player 1 has more steps than player 2, and B2 is available when the opposite is true. And Arm C places them 20% below the lower of the two virtual players. And here we have what is called a restless bandit, because not all arms are available on every pull. Player 1 has more steps than player 2 on a given day. B2 disappears from the list of potential arms available. So going back to those challenges we identified in deploying MAB agents as experience management AIs in a multiplayer setting, our proposed solution for the best choice estimation challenge is the multiplayer regression oracle. And for the reframing of the exploration challenge, we offer the multiplayer forced exploration approach. We'll go over their design for both of these and then evaluate them via simulation of this scenario. As for the multiplayer best choice estimation, single-player MAB modeling only needs to look at the metrics of a single source to determine which arm performs the best. But what is the best way for the agent to handle reward metrics generated by multiple players? Combining the players' metrics through averaging, for example, renders a loss of resolution to the data that might have been useful to the agent. Conceptually, we divide an MAB agent into 2 design pieces, an oracle and a policy. The oracle is a predictive model built from past observations that predicts future rewards for each arm. The policy is a decision process that decides when it needs to explore choices to improve the training of the oracle, or when it should instead exploit the oracle's current knowledge and go for the best right now. We're going to start our design with an epsilon greedy policy, which selects the best arm so far except epsilon % of the time when it selects another arm at random. We then set up a new oracle that holds a separate linear regression for each player. These regressions attempt to predict the next day's steps for each player based on a few features, including the player's previous steps and the net result of their achieved steps yesterday compared to those of the other teammates. Importantly, this second factor serves as a numerical representation of the comparison experience for that player, influenced by the arm that we selected. By associating these features with the observed steps for the players over several days, we're able to derive regression coefficients to make predictions for future steps for that player. The oracle builds more effective prediction capability as more observations are added. When the oracle is then consulted on which is the best arm, it averages the individual predictions for each player and the arm with the greatest predicted reward is chosen. We've shown in previous research that singular regression oracles can hold advantage over traditional approaches, and we'll include that for comparison in our evaluation as well. But the fact that the MRO maintains a multi-part regression is really key here. By keeping the player rewards separate and only averaging them at the final step of prediction, we take advantage of the full resolution of the data. And that brings us to our first experiment. So here we evaluate the performance of 5 MAB strategies within this simulation, including our modified epsilon greedy strategy with the MRO, another epsilon greedy strategy that uses a regression oracle but averages all players' data together into a single combined regression. We have a standard epsilon greedy strategy that just averages rewards, as well as the popular UCB1 and UCBT, which is a parameterless UCB variant. For the strategies that do have tunable parameters, we ran pretests to find the values for these parameters that promote the best performance in our scenario. So here are the results, where we performed 500,000 trials of the simulation with each strategy, randomizing the player models for each trial, and averaging the reward, the averaged steps of both virtual players observed at each pull. And note that for this experiment, we're looking at a horizon of 70, which reflects something we might see in actual player modeling, say once a day for 10 weeks. We also include in this table the average reward for each strategy across all pulls and the values of the final pulls. As for multiplayer exploration, to balance exploration in single-player MAB modeling, we just look at the number of times each arm has been pulled so far. But what can we do when the arm pull count might not accurately represent the exploration space of player experience? For example, consider this sequence of a 2-arm MAB that's interacting with players blue and orange over 6 pulls. The MAB can choose to place a gray third player high above both or low beneath both players. Though the agent pulled both arms an equal number of times, the players did not receive a balanced experience. The blue player received 3 upward comparisons and 9 downward comparisons in total, while the orange player received the opposite. We can't assume that balanced pulls across arms will always achieve balanced player experiences. In particular, we're interested in extending an MAB technique called forced exploration, where the MAB ensures arms are pulled as evenly as possible over a given period to better establish a baseline for each arm. In traditional forced exploration, we have an array called P that contains values denoting the number of times each arm has been pulled. Maybe we have a 3-arm bandit, and after pull number 17, we have a P array of 4, 6, 7, and we wish to engage a period of forced exploration. We're going to use the delta variance function, which simply calculates the change in variance among the values of the array if a given arm was pulled. Whatever yields the greatest reduction in variance is the arm that will achieve the most balanced exploration. For multiplayer forced exploration, we add a second array we call C, which denotes the frequency of intervention cases experienced by the players that are relevant to our model. The C array consists of as many values as there are intervention states relative to each player. In our example, the C array might reflect the number of upward comparisons experienced by player 1, the number of downward comparisons experienced by player 1, and so on for player 2. We then propose a modified exploration score that looks at the delta variance in both arrays, and we add a set of weights, WC and WP, to allow tuning for a given scenario. The arm that yields the highest exploration score is then selected to provide the most balanced exploration. Note that traditional forced exploration is the same as this equation, but with WC equal to 0 and WP as any positive number. Therefore, if we can demonstrate higher performance in strategies with a WC-WP ratio higher than 0, it supports our inclusion of this C array term within the formula. Our second experiment explores the potential influence of the WC-WP ratio. This experiment conducts 100 sub-experiments, again each with 500,000 trials and a horizon of 70, of a standard epsilon greedy strategy where the first 8 pulls employ our MFE approach. In each sub-experiment, WC and WP are selected randomly from between 0 and 3. The average rewards resulting from each are aggregated and standardized, resulting in this scatter plot showing the WC-WP ratio along the x-axis and the performance of the strategy using the ratio along the y-axis. We can see that in general, a higher ratio corresponds to higher performance, perhaps with diminishing returns, but most important is the apparent threshold for a ratio below 0.38. We suspect that this threshold depends on the particulars of the scenario, but we do see that any strategy using traditional force exploration, as a WC of 0, would present below this threshold. And this supports our argument for the inclusion of the C-array term in the force exploration formulation for multiplayer scenarios. Wrapping things up, our primary contribution in this paper is a framework for addressing the challenges of implementing an MAB-based AI as a multiplayer modeling solution. We identified the primary challenges around what it means to both explore and exploit when working with rewards for multiple players. We saw our MRO strategy outperform traditional strategies as well as a single model regression oracle. We believe its success was primarily due to keeping separate models for each player and aggregating them only at the prediction stage, where it was able to make use of the higher level of resolution offered by the data. As for the multiplayer forced exploration approach, we found that consideration for the intervention cases outperformed traditional forced exploration that overemphasized or only emphasized the pull frequencies. Though both factors can affect performance, we believe a threshold for these factors exists for multiplayer scenarios beneath which strategies may underperform. And in our future work, we will be extending our analysis of multiplayer scenarios beyond 2 players, where we expect these concerns will be further amplified. And again, we also plan to address the third challenge of social fairness. And finally, going beyond simulation, we are currently examining the potential for both the MRO and MFE in human user studies in the context of exergames. So again, I am Robert C. Gray, speaking on behalf of co-authors Jichen Zhu and Santiago Antonyan. Thank you very much for your interest and your time today. We're also grateful to the National Science Foundation for helping to fund this work. So thank you very much. I'd love to take questions.